Right now, the sun is dying. Not in the way that word might first land, not with violence, not with warning, not with any signal that could reach you before the end. It is dying the way all fires die slowly from the inside, consuming the only fuel it was ever given. At this exact moment, the sun is fusing approximately 600 million tons of hydrogen into helium every single second. That number is so large, it becomes meaningless without a frame of reference. So consider this: if you took every ocean on Earth, all of them combined, every drop of water across every sea, every trench, every frozen polar cap melted into liquid, you would still not have enough mass to account for what the sun burns through in a single day. And it has been doing this for 4.6 billion years. Yet even that is not what should stop you. What should stop you is the arithmetic. The sun contains a finite amount of hydrogen. Finite. That word carries a weight that most people allow to pass through them without resistance, the way light passes through glass, leaving no mark. But the sun's fuel supply is not infinite. It is countable. It is measurable. And when you do the measuring, when you sit with the numbers long enough to feel what they actually mean, you arrive at a conclusion that astronomy has confirmed, and that the universe has never once tried to hide from us every single star you have ever seen, every point of light that has ever decorated a human night sky, every fire that has ever burned in the cosmos. All of it is temporary. Not temporary the way seasons are temporary, temporary the way everything is temporary when the universe is given enough time to do what it does. The night sky, in other words, is not a permanent feature of reality. It is a phase, a brief, radiant, almost impossibly rare phase in the long story of a universe that was dark before the first star ignited and will be dark again, far darker, and for far longer after the last one fades. We are living inside that phase right now. We have always lived inside it. And because we have never known anything else, we have made the mistake of assuming that the light is the default condition of the cosmos, that stars are simply what space contains, that the universe is. Et it cor a luminous place. It is not. The light is the exception, the darkness is the rule. But here is what most people have never fully confronted. The death of the stars is only the beginning of the story. What comes after the long, silent, incomprehensibly vast aftermath that follows the last light makes the current age of the universe look like the opening flicker of a match held against geological time. The universe will exist for durations so enormous that every number you have ever encountered in your life, every figure that has ever seemed large, becomes not just small, but essentially zero by comparison. And through those durations, the cosmos will pass through stages that no human language was designed to describe, stages in which the familiar rules of matter, energy, and even time itself are rewritten, stages that end not with a bang or a collapse, but with something far stranger and far more final. The question at the center of this journey is one that physicists have spent over a century attempting to answer with the cold precision of mathematics, and that philosophers have spent far longer attempting to answer with something else entirely. What happens when the universe runs out of time? Not the universe as we know it, not the bright, noisy, star-filled cosmos that has surrounded us since before our species had words, but the universe itself, the full span of everything that exists, given every second it will ever be given. What does the end of everything actually look like? If you find yourself drawn to questions that make the familiar suddenly feel strange, questions that take the ceiling off your sense of scale and replace it with something that has no ceiling at all, then do something small for this channel. Hit that like button, and if you haven't already, subscribe. It costs you nothing, and it genuinely helps this work reach others who need it. Now, find somewhere comfortable, settle in, because what follows is not a short journey, and it will not leave you exactly as it found you. Let's begin. To understand where the universe is going, you first need to understand where it is right now, and why right now is so extraordinary that the odds of any civilization ever witnessing it are almost too small to calculate. We are living in what cosmologists call the Stelliferous Era. The word comes from the Latin for star-bearing, and it describes the current epoch of cosmic history, the age in which stars exist. This sounds obvious to the point of being unremarkable. Stars exist. Of course they do. Look up on any clear night, and the evidence is everywhere. But the Stelliferous Era is not the default state of the universe. It is not what the universe looked like before, and it is emphatically not what the universe will look like after. It is a window, a specific bounded temporary window during which the conditions necessary for stellar ignition align and matter burns. That window opened approximately 200 million years after the Big Bang, when the first generation of stars, enormous short-lived giants made almost entirely of hydrogen and helium, collapsed out of primordial gas clouds, ignited. Before that moment, the universe was dark, not dim, not twilight. Dark in the way that a space with no photons anywhere is dark, which is a darkness so complete that the word itself feels inadequate. For 200 million years, the cosmos existed without a single source of light, a period astronomers call the Cosmic Dark Ages, and it was the natural condition of matter, before the instability of gravity did what gravity always eventually does, and pulled things together until they burn. The window will close. This is not a hypothesis. It is a direct consequence of the laws of physics as we currently understand them, and those laws have given us no reason to expect exceptions. Stars form when clouds of gas, primarily hydrogen, collapse under their own gravity until the pressure and temperature at the core become high enough to initiate nuclear fusion. In fusion, hydrogen nuclei are forced together to form helium, and the energy released by that process pushes outward against the inward pull of gravity, creating the balance that defines a stable star. The Sun has maintained this balance for 4.6 billion years. It will maintain it for approximately another 5 billion before the hydrogen in its core runs out, at which point the Sun will expand into a red giant engulfing Mercury, Venus, and almost certainly Earth before eventually shedding its outer layers and leaving behind a dense cooling remnant the size of a planet. That remnant, a white dwarf, will not generate new energy. It will simply radiate away the heat it already contains, like an ember removed from a fire glowing for billions of years before finally going dark. But the Sun is not what should concern you in terms of the end of stars. The Sun is a medium-sized star, unremarkable in most ways, burning through its fuel at a rate that gives it a total lifespan of roughly 10 billion years. There are stars far more massive that burn through their fuel in mere millions of years, living fast and dying in spectacular supernova explosions that seed the galaxy with heavy elements. And there are stars far less massive, the red dwarfs that burn so slowly and so efficiently that they will still be fusing hydrogen long after the Sun has gone cold. Red dwarf stars are the universe's most patient fires. The smallest of them, with masses around 8%, that of the Sun, burn at temperatures so low they glow a deep, dim red. They fuse their hydrogen so slowly and circulate their fuel so completely throughout their interiors that they will live for durations that genuinely resist comprehension. A red dwarf at the lower end of the mass spectrum will remain on the main sequence, actively fusing hydrogen for approximately 10 trillion years. That is 1,000,000,000,000,000,000,000 years. The current age of the universe is approximately 13.8 billion years. A single low-mass red dwarf will outlive the current age of the universe by a factor of more than 700. To feel the scale of that comparison, consider this. If the current age of the universe were compressed into a single calendar year, 1 year, January to December, then a low-mass red dwarf would still be burning at the end of year 700. Everything that has ever happened in the history of the observable cosmos, every star formation, every galaxy collision, every supernova, every civilization that has ever existed or ever will exist under a sun like ours, would fit inside the first day and a half of that 700-year span. We are in cosmological terms at the very beginning, and yet even the red dwarfs will end. Even the most patient, most efficient, most long-lived stars in the universe will eventually exhaust their fuel, because the fuel is finite. It has always been finite. The hydrogen that filled the universe in the moments after the Big Bang is not being replenished. Every fusion reaction that has ever occurred in every star that has ever burned has permanently converted some of that hydrogen into heavier elements. The universe's hydrogen budget is being spent slowly but irreversibly with every second that passes. Astronomers estimate that the Stelliferous Era, the full span of time during which stars will actively form and burn, will last for somewhere between 1 trillion and 100 trillion years, depending on how efficiently the last remaining gas clouds are converted into red dwarfs. After that, no new stars will ignite. The raw material will be gone. Some stars will still be burning. The longest-lived red dwarfs will persist well into this range, but no new ones will be born to replace them. The galaxy will begin to go dark one star at a time over durations that make the current age of the universe look like an afterthought. The last star will die in silence. Not with an explosion. Red dwarfs don't explode. They simply cool. They transition from active fusion to inert remnant over billions of years, their light dimming so gradually that there would be no single moment you could point to and say that was the last light. It would be more like watching a sunset in which the sun takes 1 trillion years to touch the horizon, and then eventually it does. What comes after that is something the human mind was not built to imagine, but we are going to try anyway. The stars around you right now are not all the same age. They are not burning the same fuel at the same rate, and they will not die in the same way or at the same time. The night sky, which presents itself as a unified ceiling of light, is in reality a crowd of individuals at wildly different stages of their lives. Some only millions of years old, some billions, some so ancient that they formed when the universe was a fraction of its current age, and have been quietly burning ever since. Looking up at the stars is not looking at a static image. It is looking at a population in motion, a community of fires at different points in their stories, and the story of each one ends the same way in darkness, but arrives there through paths so different from one another that understanding those paths is essential to understanding what the universe is actually doing over time. The most massive stars burn with a ferocity that is almost self-destructive. A star with 30 times the mass of the sun is not 30 times as bright. It is tens of thousands of times brighter, burning through its hydrogen fuel at a rate so extreme that its entire lifespan is measured not in billions of years, but in millions. A few million years is nothing on the scale of cosmic time. It is less than the blink of an eye. The Himalayas are older than a massive star's entire lifespan. These enormous stars live fast and end catastrophically collapsing, and then rebounding in supernova explosions that for a brief period can outshine entire galaxies. A single supernova can release more energy in a few seconds than the sun will radiate across its entire 10 billion year life. What remains afterward is either a neutron star, a city-sized object so dense that a teaspoon of its material would weigh more than 1 billion tons on Earth, or, if the original star was massive enough, a black hole. These are the universe's most dramatic actors, and they exit the stage almost as quickly as they arrive. At the other end of the spectrum sit the stars that will outlast almost everything, the red dwarfs. These are the quiet ones, the patient ones, the stars that burn so gently that if you could stand on a planet orbiting one, the star would appear not as a brilliant white disk like our sun, but as a dim, rust-colored ember taking up perhaps twice the width of the sun in the sky, casting a light more like late afternoon than midday. Red dwarfs are the most common stars in the galaxy by an enormous margin. Roughly 70% of all stars in the Milky Way are red dwarfs. They are everywhere, and yet most of them are invisible to the naked eye because none of them are bright enough to see without a telescope. Not one. The nearest star to Earth after the Sun is Proxima Centauri, located 4.24 light-years away, approximately 25 trillion miles, and it is a red dwarf. If you replace the Sun with Proxima Centauri, the Earth would be in the freezing darkness. To be warm enough for liquid water, a planet would need to orbit a red dwarf at a distance so close that it would be gravitationally locked, one side permanently facing the star, one side permanently turned away, a world of eternal day and eternal night with a thin temperate ring between them. Whether life could survive in such conditions is a question that science has not yet answered. But the question matters because if it can, then red dwarf planets are where the universe's last ecosystems might exist, orbiting its last stars in the last warmth that reality will produce. A red dwarf with half the mass of the Sun will live for approximately 56 billion years. The universe is currently 13.8 billion years old, which means a star of this type born at the same time as the Big Bang would today be barely 1/4 of the way through its life. It has not even reached middle age. A red dwarf with 1/10 the mass of the Sun will live for approximately 10 trillion years, and the smallest red dwarfs, those hovering just above the minimum mass required for hydrogen fusion, about 8% of the Sun's mass, may burn for as long as 10 to 100 trillion years, and their lifespans so extended that comparing them to our Sun's lifespan is like comparing the height of a mountain to the thickness of a piece of paper. Now, consider what those numbers mean for the universe's story. The Stelliferous Era, the full age of stars, will span roughly 100 trillion years by most estimates. Of that vast period, the first 13.8 billion years, everything that has happened so far, everything we know about every galaxy, every civilization, every war and love and discovery in the history of our species, occupies approximately 0.014% of the total duration. If you printed the timeline of the Stelliferous Era on a roll of paper stretching from New York to Los Angeles, the entirety of current cosmic history would fit within the first few feet after the starting line. Everything else, the remaining 99.986% of the age of stars, lies ahead, in a future we will never see populated by fires. We will never know. Somewhere in that future, the last star will form. Astronomers believe that star formation in the Milky Way has already slowed dramatically compared to its peak roughly 10 billion years ago. At that time, the galaxy was converting gas into stars at a rate perhaps 10 times higher than today. The gas clouds that fuel star birth are being consumed faster than the processes recycling stellar material can replenish them. The interstellar medium is not a static reservoir. It is being slowly drained. New stars form from old gas, and old gas comes partly from the material shed by dying stars, but the efficiency of this recycling is not 100%. Some material is locked away permanently in stellar remnants. Some escapes the galaxy entirely. The net result is a gradual decline in star-forming activity, not a sudden cutoff, but a slow fade, the galaxy becoming quieter and quieter over trillions of years as the raw ingredients for new stars grow sparse. At some point, the last stellar nursery will form its last cluster. The last protostellar cloud will collapse. The last nuclear fire will ignite, and then no new fires will follow. What remains at that point will be whatever stars were already burning, primarily red dwarfs, slowly cooling toward their ends over the incomprehensible spans of time their low-mass fuel supplies allow. Think of the galaxy at this stage as a city after midnight, most of its windows dark, a few scattered lights still burning in apartments where someone is still awake, and then one by one, those last lights going out. Except in this case, the city is hundreds of thousands of light years across, and some of those last lights will burn for another 100 trillion years before they finally dim. There is something in this image that refuses to leave quietly. The idea that somewhere in the galaxy's future there exists a last star, a specific individual fire, a red dwarf, so small and so patient that it outlives every other burning object in the Milky Way, the final inheritor of all the hydrogen that the galaxy has not yet spent. It has no name, it has no catalog designation, it may not yet exist, it might form billions of years from now, from one of the last remaining gas clouds. But it is real in the sense that physics requires it. There must be a last star because there are a finite number of them, and one of them will be last. What will it illuminate? By the time this final star is burning the galaxy, as we know it will be unrecognizable. The Milky Way and the Andromeda Galaxy will have long since collided and merged, a process already underway and expected to complete in roughly 4 billion years. The combined galaxy, which astronomers sometimes call Milkomeda, will have reshaped itself through the violence of that merger into a large elliptical galaxy. Its spiral arms erased its star formation, largely quenched by the disruption. Most of the sun-like stars will be long dead. Most of the stellar remnants, the white dwarfs, the neutron stars will be cooling quietly in the dark. The supermassive black hole at the center will be feeding on whatever material remains in its vicinity, growing slowly, radiating, nothing visible to any eye that might still exist to see. The planets that once orbited sun-like stars will still be drifting in space if they haven't been gravitationally scattered into the void. They will be frozen, their surfaces at temperatures approaching absolute zero, their atmospheres long since stripped or frozen solid. No sunlight warms them. No volcanic heat reaches their surfaces in sufficient quantities to matter. They are the fossils of solar systems, remnants of a warmer age, preserved by the simple fact that nothing has yet destroyed them. The last red dwarf burns on. Its light deep red would be barely visible to eyes calibrated for our sun. It radiates perhaps a 10,000th of the sun's luminosity. It produces no dangerous ultraviolet radiation, no powerful stellar flares capable of sterilizing a close orbit, or perhaps it does in its youth, but by the time it has aged to this point in the universe's story, even its flare activity has quieted. It is the calmest, dimmest, most enduring fire the universe knows how to make. Sitting with this image, the last star in a galaxy of cooling remnants and frozen worlds produces a kind of feeling that doesn't map cleanly onto any single emotion. It is not sadness exactly. It is something more like the feeling of standing in a cathedral long after the last service has ended, when the candles have burned to their bases and the echoes have finally stilled, and you are left with the architecture of something that once held, meaning its structure still intact. Its purpose now suspended in a silence that has no end. The last red dwarf will not explode. It will not go supernova. It lacks the mass for anything so dramatic. When its hydrogen is finally exhausted, it will contract slightly, its surface brightening briefly in a blue-white flash, as it becomes what astronomers call a blue dwarf, a transitional phase that no red dwarf has yet reached because the universe is not old enough for any of them to have gotten there. Then over billions of additional years it will cool into a white dwarf, a crystallized sphere of degenerate carbon and oxygen the size of a large planet containing the ash of the last stellar fire, no longer generating energy, simply radiating away the warmth it has accumulated over its impossibly long life. And then slowly over timescales that the next sections of this journey will attempt to make real, even that warmth will fade. This is only the beginning. The end of the Stelliferous Era, the final cooling of the last red dwarf, is not the end of the universe. It is not even close. When the last star fades, the universe will be approximately 100 trillion years old. That sounds like a conclusion. It sounds like the final chapter. But measured against what comes next 100 trillion years is barely a prologue. The universe after the stars is a universe that will persist for durations so much larger that everything we have discussed so far, the entire age of stars from the first ignition to the last ember, will shrink to an almost invisible point at the very beginning of the cosmic timeline. What comes next is a world without fire, without light, without the energy gradients that make complexity possible. And yet it is a world that will last in its own cold and quiet way for far longer than any fire ever burned. The darkness is not an ending. It is the beginning of something far stranger. 0831, Claude responded. When the last red dwarf finally exhausts its hydrogen and begins its long cooling into darkness, the universe will enter a phase that has no analog in anything. When the last red dwarf finally exhausts its hydrogen and begins its long cooling into darkness, the universe will enter a phase that has no analog in anything human experience has prepared you for. There will be no dramatic announcement, no final explosion visible across the cosmos, no moment that any hypothetical observer could point to and say that was the transition. The Stelliferous Era will simply end the way it began, gradually, locally, one fire at a time until the last fire is gone, and what remains is a universe populated not by burning stars but by their corpses. Astronomers call this the Degenerate Era. The word degenerate here carries no moral weight. It is a precise technical term describing the physical state of matter under extreme compression. When a star like the Sun exhausts its nuclear fuel, the outward pressure that once balanced gravity disappears. Gravity wins as it always eventually wins, and the stellar core collapses inward. But for stars below a certain mass threshold, roughly 8 times the mass of the Sun, the collapse is halted before it becomes catastrophic. It is halted by a quantum mechanical effect called electron degeneracy pressure. In a white dwarf, electrons are packed so tightly that quantum physics forbids them from occupying the same energy state simultaneously, and this resistance to further compression creates a pressure that holds the star up against gravity, without requiring any ongoing nuclear reactions at all. A white dwarf generates no new energy. It is not burning, it is not fusing. It is simply a sphere of crystallized matter, mostly carbon and oxygen, roughly the size of Earth, but containing roughly the mass of the Sun, held rigid by the laws of quantum mechanics and slowly radiating away the heat trapped inside it from its earlier life. If you could hold a fragment of white dwarf material in your hand, which you could not, because a piece the size of a grape would weigh approximately as much as a car, it would feel like a hot coal slowly losing its warmth. Except the timescale on which it loses that warmth is not hours. It is not years. It is not millions of years. It is trillions of years. The universe is currently 13.8 billion years old, and not a single white dwarf anywhere in the observable cosmos has had time to cool completely. Every white dwarf that has ever formed is still warm. The oldest ones, the first ones, produced by the earliest generation of Sun-like stars, have been cooling for over 10 billion years and are still radiating faint heat detectable by telescopes. They have barely begun. The cooling curve for a white dwarf is so gradual that a white dwarf formed today would take somewhere between 1 quadrillion and 1 quintillion years to approach the temperature of the surrounding space. That is between 1,000 trillion and 1,000,000 trillion years. The current age of the universe does not appear in that number in any meaningful way. To feel what a quadrillion years actually means relative to what you know, consider this. If every second since the Big Bang represented 1 year, you would need to count for approximately 4,400,000 years just to reach the present day. To count to a quadrillion at that rate, you would need more than 31 million years of continuous counting. The number is not large in the way that a tall building is large, something you can look up at and feel the scale of in your body. It is large in the way that makes the comparison itself feel like a category error. And yet in the Degenerate Era, a quadrillion years is not extraordinary, it is ordinary. During this vast period, the observable universe will be populated primarily by 3 types of objects: white dwarfs, neutron stars, and black holes. The white dwarfs will be cooling, slowly losing heat to the surrounding darkness. The neutron stars, the remnants of more massive stars that died in supernova explosions, compressed not just to the density of white dwarfs but far beyond to the density of atomic nuclei, will also be cooling, radiating away the enormous heat generated by their violent formation. A neutron star contains roughly 1 to 2 times the mass of the Sun, compressed into a sphere approximately 12 miles across. A sugar cube of neutron star material would weigh approximately 1 billion tons. They are among the densest objects in the known universe, second only to black holes, and they cool over timescales similar to white dwarfs, fading from intensely hot objects to cold, dark, frozen remnants over trillions of years. But here is what makes the Degenerate Era strange in a way that goes beyond the numbers. The universe will be dark, not simply dim, not lit by faint stars, genuinely dark in the way that a room with no light source is dark. The only photons traveling through space will be the ancient redshifted remnants of earlier eras, the cosmic microwave background radiation by then, so stretched by the expansion of the universe that its temperature will have dropped from its current 2.7 Kelvin to temperatures so low they are essentially indistinguishable from absolute zero. White dwarfs and neutron stars will still radiate some faint heat, but that radiation will be so dim, so cold, so spread across such incomprehensible distances that the universe will be, for all practical purposes, a dark place. An enormously vast, almost perfectly dark place populated by dense cold objects, drifting silently through expanding space. The galaxies themselves will have changed. By the time the Degenerate Era begins in earnest, the Milky Way and Andromeda will have long since merged. The combined galaxy will have evolved over trillions of years through a process called dynamical relaxation, in which gravitational interactions between stellar remnants gradually redistribute their energies. The most massive remnants will tend to sink toward the galactic center. The lightest objects will tend to be flung outward to the edges or ejected entirely from the galaxy. Over timescales of roughly 10 to the 19th power years, that is a 1 followed by 19 zeros, most of the stellar remnants currently in galaxies will have been ejected into intergalactic space through these gradual gravitational interactions. The galaxy will dissolve not violently, but through the patient arithmetic of orbital mechanics repeated over unimaginable timescales. What remains at the center will be the supermassive black hole that was always there, grown larger by the slow accumulation of material over the eons, surrounded by a dwindling population of stellar remnants still loosely bound to it. The rest, the vast majority of white dwarfs and neutron stars that once made up the galaxy, will be drifting alone in intergalactic darkness, separated from one another by distances that dwarf even the current separations between galaxies. The universe will not merely be dark, it will be almost unimaginably empty of anything except these cold, silent drifters. Now consider what happens to those white dwarfs over timescales even longer than the ones already described. There is a theoretical prediction in particle physics that protons, the positively charged particles at the heart of every atomic nucleus, the fundamental building blocks of all the matter you have ever encountered, may not be eternal. The standard model of particle physics, as currently understood, does not predict proton decay, but extensions of the standard model, particularly theories attempting to unify the fundamental forces into a single framework, do. If protons decay, they do so with a half-life estimated at somewhere above 10 to the 34th power years to a 1 followed by 34 zeros. This number is so large that even framed against the Degenerate Era, it represents an enormous span of time. But if protons decay even on that timescale, the implications for white dwarfs and neutron stars are profound. These objects are made of matter, ordinary matter, just in exotic forms and extreme densities. If the protons within them slowly decay into lighter particles over these immense timescales, then white dwarfs and neutron stars will gradually dissolve, not collapse, not explode, dissolve, their material converting slowly to lighter particles and radiation over periods that make the current age of the universe look like a rounding error. If proton decay does not occur, if protons are truly stable, then white dwarfs will persist essentially indefinitely, slowly cooling toward the temperature of the universe around them, eventually becoming what astronomers call black dwarfs. Cold, dark, inert spheres of crystallized carbon and oxygen, indistinguishable from the surrounding darkness, because they radiate essentially no energy. It has been estimated that no black dwarf yet exists anywhere in the universe, because the universe is not old enough for any white dwarf to have cooled sufficiently. They are the universe's future, not its present. An entire population of objects that have never yet existed waiting at the end of timescales we can write in notation but cannot feel. Whether matter dissolves through proton decay or persists as cold, dark remnants, what the Degenerate Era makes clear is this: the universe does not end when the stars go out. It continues. It continues for far longer than the age of stars populated by objects that neither burn nor glow but simply exist, cooling and drifting through expanding darkness with a patience that has no human analogue. The Degenerate Era is the universe's long exhale, the slow release of all the heat accumulated during the Age of Fire, spread across timescales that reduce all of stellar history to a brief, bright opening. Through all of this, one category of object persists without cooling, without dissolving, without fading in any conventional sense. One type of remnant that the Stelliferous Era left behind, which does not obey the same slow decline as white dwarfs and neutron stars, which grows rather than shrinks, which gains energy rather than losing it, which dominates the gravitational landscape of the post-stellar universe with an authority that nothing else can match. The black holes. They have been there all along, from the stellar mass black holes born in supernova explosions to the supermassive black holes lurking at the centers of galaxies containing millions or billions of solar masses compressed into regions smaller than our solar system. They do not burn. They do not radiate in any conventional sense. They simply sit at the bottom of the deepest gravitational wells in existence, consuming whatever matter, and radiation falls within their reach, growing slowly, outlasting everything around them. During the Degenerate Era, as white dwarfs cool and neutron stars fade and stellar remnants drift apart, the black holes persist. They absorb the faint radiation of the cooling universe. They consume the occasional white dwarf or neutron star that drifts too close. They wait with a patience that is not patience at all, because patience implies awareness of waiting, and black holes are aware of nothing. They simply exist, and the universe has no mechanism to end them on short timescales. No mechanism, that is, except one, and that mechanism will eventually erase every black hole in the universe. But to understand how, you first have to understand something about the nature of black holes that remained hidden from physics until the 1970s, when a young British physicist sitting with a calculation he had begun almost as an intellectual exercise arrived at a conclusion so strange and so consequential that it took the scientific community years to fully accept it. The conclusion was this: black holes are not truly black. They radiate, they lose mass, and given enough time, they evaporate completely. The universe, it turns out, has a plan for even the darkest and most patient objects it contains. But the timescales involved make everything discussed so far, the entire Degenerate Era, the quadrillions and quintillions of years of cooling remnants drifting through expanding darkness, look by comparison like the opening seconds of a story that has barely begun. In 1974, a 32-year-old physicist named Stephen Hawking sat with a calculation that he had not expected to produce anything interesting. He was working on the intersection of two fields that had rarely been brought into conversation with each other: quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales, and general relativity, Einstein's theory describing gravity and the large-scale structure of space-time. Most physicists of the era treated these two frameworks as separate tools for separate problems. Quantum mechanics described the world of particles and fields. General relativity described the world of massive objects and curved space. The two theories were each extraordinarily successful within their own domains, but they were mathematically incompatible in ways that no one had yet resolved. Hawking was attempting something more modest than resolving that incompatibility. He was simply trying to understand what quantum mechanical effects might look like near the boundary of a black hole, the event horizon, that point of no return beyond which nothing, not even light, can escape. The calculation was exploratory. It was the kind of theoretical work that physicists do when they want to understand the implications of their equations in extreme conditions, not necessarily expecting a dramatic result. What he found stopped him. The calculation showed that black holes should radiate. Not in some metaphorical sense, not as a theoretical curiosity without physical consequence, but genuinely measurably thermodynamically radiate, emitting a spectrum of particles in a manner almost identical to the radiation emitted by a hot object. The black hole, according to the mathematics, had a temperature, and because it had a temperature, it had to lose energy over time, the way any warm object loses energy to a cooler environment. And because mass and energy are equivalent, this is what Einstein's most famous equation, E equals mc squared, means in practice. Losing energy meant losing mass. The black hole was evaporating. This result was so unexpected, so contrary to the prevailing understanding of black holes as purely consuming objects from which nothing could ever escape, that Hawking himself initially doubted it. He checked the calculation. He examined the assumptions. He looked for the error that would make the result go away. It did not go away. What became known as Hawking radiation was real, at least as real as any theoretical prediction can be, before experimental confirmation and the mathematics supporting it were and remain among the most robust in theoretical physics. The mechanism behind Hawking radiation is rooted in a feature of quantum mechanics that has no classical analog. Empty space is not empty. This is not a poetic statement. It is a precise description of what quantum field theory tells us about the vacuum. At every point in space, even in regions containing no particles, no matter, no radiation of any kind, quantum fields fluctuate. These fluctuations are not random noise without consequence. They have the capacity to briefly produce pairs of particles, a particle and its corresponding antiparticle, which spontaneously appear out of the energy of the vacuum, exist for an almost inconceivably brief moment, and then annihilate one another, returning their borrowed energy to the vacuum. This process happens everywhere continuously, and under ordinary circumstances it is undetectable because the particle pairs recombine before they can be measured. Near the event horizon of a black hole, something different can happen. If a particle pair appears at precisely the right location, one particle just inside the horizon, one just outside the geometry of spacetime, near the black hole, can separate them before they have the opportunity to recombine. The particle inside the horizon falls into the black hole. The particle outside escapes into space. From the perspective of a distant observer, the black hole appears to have emitted a particle as if it were radiating, and because energy cannot be created from nothing, the energy of the escaping particle must come from somewhere. It comes from the black hole itself. The black hole loses a tiny, almost inconceivably small amount of mass with each emission. Over time, this process repeated with incomprehensible frequency across the entire surface of the event horizon causes the black hole to shrink. The rate of this evaporation depends on the black hole's mass. Smaller black holes are hotter and evaporate faster. Larger black holes are colder and evaporate more slowly. The temperature of a black hole is inversely proportional to its mass, which means that as the black hole loses mass and shrinks, its temperature rises, which causes it to evaporate faster, which raises its temperature further in a cascade that accelerates toward the end. The final moments of a black hole's evaporation are not a quiet fade, but a burst, a flash of high-energy radiation as the last of its mass converts to energy in a brief, brilliant explosion. After that burst, nothing remains. Not a remnant, not an ash, nothing. Now consider the timescales. A black hole with the mass of the Sun would take approximately 2 × 10 to the 67th power years to evaporate completely through Hawking radiation. That is a 2 followed by 67 zeros. Written out in full, that number would occupy more than a line of text on its own. It is approximately 5 million trillion times the current age of the universe. And yet, a solar mass black hole is not large by the standards of black holes. It is, in fact, quite small. The supermassive black holes at the centers of galaxies contain masses ranging from millions to billions of times the mass of the Sun. The black hole at the center of the Milky Way, known as Sagittarius A star, contains approximately 4 million solar masses. The black hole at the center of the galaxy M87, which became famous in 2019 when the Event Horizon Telescope produced the first direct image of a black hole's shadow, contains approximately 6.5 billion solar mass. These objects are not just larger than stellar mass black holes. They are so much larger that the evaporation timescale scales not linearly but with the cube of the mass, meaning that a black hole 10 times more massive takes not 10 times longer to evaporate, but 1,000 times longer. The evaporation time for a black hole with the mass of Sagittarius A star, 4 million solar masses, is approximately 10 to the 83rd power years, a 1 followed by 83 zeros. The evaporation time for a black hole with a mass of 1 billion solar masses toward the larger end of what has been observed is approximately 10 to the 99th power years, a 1 followed by 99 zeros. These are not numbers that yield to analogy in any satisfying way. Every comparison that might make them feel comprehensible ultimately fails, because the human mind did not evolve to feel the difference between 10 to the 67th and 10 to the 99th. Both are simply enormous, and the fact that the second is 10 to the 32nd times larger than the first, a factor of 100 million trillion, does not register emotionally in the way that the difference between a mile and 1,000 miles registers. The only honest thing to say about these numbers is that they are larger than anything else in this story so far, including the entire Degenerate Era, with its quadrillions and quintillions of years of cooling remnants, and that they dwarf even those durations the way the observable universe dwarfs a single proton. But they are finite. This is the point that carries all the weight. However large these numbers are, they are not infinite. They are specific, they are calculable, and they will in the fullness of time be reached. During the black hole era, the universe will be a place of almost absolute darkness. The white dwarfs will have either dissolved through proton decay or cooled to temperatures indistinguishable from the surrounding space. The neutron stars will be similarly dark and cold. The only objects still doing anything of consequence, the only structures still evolving in any meaningful sense will be the black holes, and what they will be doing imperceptibly slowly is shrinking. The universe will be expanding all the while. The space between things will be growing. Objects not gravitationally bound to one another, which by this point means almost everything since the galaxies will have dissolved and their remnants scattered, will be drifting apart at rates determined by the continued expansion of space-time itself. The universe will be growing larger and emptier and colder with every moment. The cosmic microwave background radiation, already at a temperature of 2.7 Kelvin today, will have dropped to temperatures so small they require scientific notation to express fractions of a degree above absolute zero. The universe will be in every meaningful thermal sense essentially at equilibrium with the cold of empty space, except for the black holes, which will still be slightly warmer than their surroundings, still radiating their faint Hawking radiation into the void. In the early part of the black hole era, the smaller black holes, stellar mass objects formed from individual dying stars, will evaporate first. Over timescales of 10 to the 67th to 10 to the 70th years, these smaller objects will complete their evaporation, each ending in that brief burst of high-energy radiation that briefly outshines anything in its local universe before vanishing entirely. These flashes will be the last events of any energy significance occurring in their regions of space. After each flash, the region around it will return to an even deeper darkness than before, because the object that had been the local source of Hawking radiation, however cold and faint, will be gone. The supermassive black holes will persist long after the stellar mass ones have evaporated. They will be the last objects in the universe still doing anything observable. For timescales stretching to 10 to the 100th power years and beyond, what physicists sometimes call a googol of years, since the number 10 to the 100th is the origin of that word, the supermassive black holes will sit at the centers of what were once galaxies, in regions of space so empty and so cold that they might as well be alone in the universe, slowly losing mass, slowly shrinking, slowly warming as their mass decreases and their Hawking temperature rises. And then one by one they too will reach the end. The final moments of a supermassive black hole's evaporation would, if there were any observer left to witness it, be extraordinary. For most of its existence, a large black hole radiates so slowly and at such low temperatures that it is effectively invisible. But as its mass drops below a certain threshold, the cascade of evaporation accelerates, the temperature climbs, the radiation brightens. In the last fraction of a second of its existence, the black hole releases the remainder of its mass energy in a burst of high-energy gamma rays and other particles, a final brief ferocious flash of light in a universe that has otherwise been dark for longer than words have any right to describe. Imagine standing if you could stand, if matter capable of standing still existed in the vicinity of the last black hole in the universe. Around you in every direction is darkness and cold. The expansion of space has carried everything so far apart that the nearest other object, whatever frozen remnant it might be, is separated from you by distances that light has not had time to cross since the Stelliferous Era ended. The universe is quiet in a way that the word quiet cannot capture, because quiet implies an absence of sound that could in principle return, and this silence has no return. It is the silence of a universe that has finished everything it was going to do except for this one last thing. The black hole is small now, smaller than it has been since the moments after the Big Bang. Its temperature is rising. It is radiating more brightly than it has at any point in its billions upon billions of years of existence. The Hawking radiation is no longer a trickle, but a cascade, each second releasing more energy than the previous second. the final explosion of a process that began when the first massive star died and left behind a darkness that the universe has been slowly, patiently, inevitably dissolving ever since. And then it flashes. For perhaps a fraction of a second, the final black hole outshines everything that remains in the observable universe. A burst of gamma rays, electrons, positrons, and other particles expands outward into the void at the speed of light, carrying with it the last mass energy that was ever concentrated into a single object. The radiation disperses. The particles scatter into the expanding darkness. The region where the black hole existed is now indistinguishable from every other region of space. The black hole era is over. The universe is for the first time in its history genuinely without structure. No stars, no remnants, no black holes, no concentrations of mass anywhere. Just an expanding void of cooling radiation and scattered fundamental particles thinning further, with every moment as space continues to grow. What comes next has no name in any human language that predates cosmology. It is a state of existence so alien to anything in human experience that even the physicists who have thought about it most carefully tend to fall quiet when pressed for description. Not because it is frightening, but because it is so far beyond the reach of metaphor that the usual tools of communication simply stop working. It is the Dark Era, and it is where the universe will spend by an almost incomprehensible margin most of its existence. 0834, Claude responded. The universe after the last black hole evaporates is not a universe in any sense that the word has ever been used before. The universe after the last black hole evaporates is not a universe in any sense that the word has ever been used before. Every definition of universe that human thought has produced a collection of matter and energy, a place where things happen, a system with structure and dynamics and change, requires the existence of something, some concentration of mass, some gradient of energy, some difference between one region of space and another that allows events to occur, that allows one state to transition into a different state, that allows time itself to mean something beyond a parameter in an equation. After the black hole era ends, the universe has none of these things. What remains is a gas, if gas is even the right word, and it is not quite, but it is the closest available of fundamental particles scattered across a space so vast that the average distance between any two particles exceeds the distances between galaxies today by factors that do not reward calculation. Photons from the final Hawking radiation bursts are spreading outward at the speed of light, thinning as they go, their wavelengths stretching as the expansion of space redshifts them toward lower and lower energies. Electrons and positrons drift alone. Neutrinos, if they are stable, move through the darkness on trajectories that will never again bring them into contact with anything. Whatever particles survive this era, whatever the final stable constituents of matter, turn out to be a question that depends on physics not yet fully understood. They drift. That is all. They drift. This is the Dark Era. To understand what makes the Dark Era so strange, stranger in a way than anything that preceded it, stranger than the death of the stars or the evaporation of black holes, you need to understand what entropy is and what it means for a physical system to approach its maximum. Entropy is one of the most important concepts in all of physics and also one of the most consistently misunderstood. It is often described as a measure of disorder, which is accurate in a loose sense, but misleading in ways that matter for this discussion. More precisely, entropy is a measure of the number of possible arrangements that a system could be in while still looking the same from the outside. A room full of gas molecules with all the molecules crowded into one corner has low entropy. There are very few arrangements of the molecules that would produce that configuration. The same room with the molecules distributed evenly throughout has high entropy. There are an enormous number of arrangements that would produce that configuration, and no particular reason for the molecules to be in any one of them rather than the others. The second law of thermodynamics states that in any isolated system, entropy tends to increase over time. This is not a law in the sense of a rule imposed from outside. It is a statistical inevitability. There are simply far more high entropy states than low entropy states, and so a system moving randomly through its possible configurations will, with overwhelming probability, move toward higher entropy. The universe began in a state of extraordinarily low entropy. The Big Bang was a highly ordered, highly concentrated initial condition, and everything that has happened since, every star that has burned, every galaxy that has formed, every organism that has metabolized, has been part of the universe's long journey toward higher entropy. Heat death is what physicists call the end point of that journey. It is the state in which entropy has reached its maximum possible value, a state of perfect equilibrium in which no region of the universe is warmer or cooler, denser or more sparse, more energetic or less energetic than any other. In a state of perfect equilibrium, no work can be done, no energy can flow, nothing can happen, not because some force prevents it, but because the universe has run out of the differences that make things happen. Events require gradients, a temperature difference that allows heat to flow, a density difference that allows matter to move, an energy difference that allows reactions to occur. Heat death is the state in which all gradients have been erased. The universe is moving toward this state. It has always been moving toward this state. Every fire that has ever burned has pushed the universe slightly further toward equilibrium by converting concentrated chemical or nuclear energy into dispersed heat. Every star that has ever shone has radiated energy into space, spreading it thinner and more uniformly across the cosmos. Every black hole that has evaporated has returned its concentrated mass energy to the universe as diffuse radiation. The dark era is the universe at the far end of this process, not quite at maximum entropy, because the scattered particles and cooling radiation still represent slight deviations from perfect uniformity, but so close that the distance remaining is almost meaningless. The particles drifting through the dark era are themselves not necessarily eternal, and this is where the physics becomes genuinely uncertain in ways that matter enormously for the long-term fate of the universe. If protons are unstable, if the extensions of the standard model that predict proton decay are correct, then the ordinary matter that survived the black hole era will not survive the dark era. Protons will decay into lighter particles, primarily positrons and neutral pions, over timescales estimated at somewhere between 10 to the 32nd and 10 to the 36th years, depending on which theoretical model is correct. These timescales sound enormous, but measured against the dark era, they are brief. The dark era will last in various theoretical estimates for timescales that extend to 10 to the 10 to the 76th power years, a number so large that it cannot be meaningfully expressed in the usual way, because the exponent itself requires an exponent. If proton decay occurs on the shorter end of the predicted range, all protons in the universe will have decayed before the dark era has barely begun. What remains after proton decay is a universe of electrons, positrons, neutrinos, and photons, all either stable or extraordinarily long-lived. These particles interact almost never. An electron drifting through the dark era might travel for timescales vastly longer than the current age of the universe before encountering another particle. When electrons and positrons do eventually find each other, they annihilate, producing two photons that then travel onward through the darkness indefinitely. Over time, the electron-positron pairs thin further, as more and more of them find each other and annihilate, until the universe becomes a sea of photons and neutrinos, losing energy to the expansion of space wavelengths, stretching toward infinity, temperatures approaching absolute zero with asymptotic patience. If protons are stable, the situation is different, but not ultimately more hopeful. White dwarfs that survived the Degenerate Era would persist as black dwarfs into the dark era, their protons intact, their matter frozen into crystalline structures at temperatures indistinguishable from absolute zero. They would drift through the expanding darkness as cold, silent spheres of inert matter, interacting with nothing, changing nothing, simply occupying space for durations that make all previous timescales seem brief. Eventually, even these objects might succumb to quantum tunneling effects. Given sufficient time, timescales written not with exponents, but with towers of exponents, quantum mechanics allows for transitions that classical physics would forbid. A cold lump of iron given enough time might quantum tunnel into a configuration of lower energy. A black dwarf, given timescales of 10 to the 10 to the 76th power years, might quantum tunnel into a black hole which would then evaporate through Hawking radiation in a final flash. But these events, if they occur at all, are so rare and so separated in time that the universe between them would be to any meaningful approximation unchanging. Here is the feature of the dark era that is hardest to communicate, and perhaps the most important to sit with. Time becomes almost meaningless. In the universe you inhabit, time has texture, it has events. Seconds are distinguishable from one another because different things happen in different seconds. Stars move, particles collide, chemical reactions proceed, thoughts occur. Time is the dimension along which change unfolds, and where there is change, time has content. In the dark era, by contrast, 1 trillion years might pass between any two events of consequence occurring within a given region of space. The expansion of the universe continues. This is perhaps the only unambiguous process still operating, but expansion itself produces no events, only increasing distances. A universe that is expanding but otherwise unchanging is a universe in which time passes without meaning, in which a second and 1 trillion years are experientially equivalent because nothing distinguishes them. This is the universe's true old age, not the active event-filled senescence of the black hole era, but a profound stillness that has no analogy in any human experience of age or rest or waiting. It is not even sleep, because sleep implies the possibility of waking. It is the state of a system that has done everything it is going to do and now simply is without narrative, without direction, without the possibility of anything mattering in any thermodynamic sense. And yet, there is one more thing to consider before accepting the dark era as the final word on the universe's fate. It is a concept so strange that even physicists who understand it well tend to express discomfort when explaining it, not because it is mathematically uncertain, it follows directly from statistical mechanics, but because it produces a conclusion so deeply counterintuitive that it feels like it must be wrong and yet cannot quite be shown to be. The concept is the Boltzmann brain. In 1896, the Austrian physicist Ludwig Boltzmann, one of the founders of statistical mechanics, a man whose life ended in tragedy, but whose ideas have outlasted everything else about his era, was grappling with a question about the arrow of time. If entropy tends to increase, why did the universe start in such a low entropy state? One idea he entertained and later rejected was that the universe might be in a state of thermal equilibrium on average, with the low entropy region we inhabit being a rare fluctuation. Statistical mechanics allows for this. In a system at equilibrium, random fluctuations will occasionally produce lower entropy configurations. Most of the time, the system remains in high entropy states, but given infinite time, every possible configuration will eventually occur, including very low entropy ones. In the dark era, given the timescales involved, this logic applies with full force. The universe in the dark era is not at perfect equilibrium. It is close but not perfect. And in a universe that is close to but not at perfect equilibrium, given enough time, random quantum fluctuations will occasionally produce structures. Most of these structures will be small and brief, a momentary clustering of a few particles that quickly disperses again. But given timescales that extend to 10 to the 10 to the 50th power years and beyond, even extraordinarily unlikely, fluctuations become not just possible but certain. A fluctuation producing a single organized particle, a fluctuation producing a molecule, a fluctuation producing over timescales so large they require notation systems not yet invented, a self-aware structure that exists for a brief moment before dispersing back into equilibrium. This hypothetical object, a conscious observer arising spontaneously from quantum fluctuations in the vacuum, fully formed with memories and perceptions that did not arise from any actual prior experience, is what cosmologists call a Boltzmann brain. It is named after the physicist whose statistical reasoning implies its eventual existence. Such an observer would open its eyes, so to speak, in a universe of perfect darkness and cold, with memories of a universe it never actually inhabited, and would dissolve back into equilibrium almost immediately. The timescale for a Boltzmann brain to arise is unimaginably large. Estimates range from 10 to the 10 to the 50th power years upward, But in the Dark Era, such timescales are not exceptional. They are the ordinary currency of time in a universe that has run out of anything else to do. Whether Boltzmann brains actually arise, and what their existence would mean philosophically, is a question that physics cannot yet fully answer. But their theoretical possibility illustrates something important about the Dark Era. It is not a universe in which nothing ever happens. It is a universe in which almost nothing ever happens. But given enough time, even almost nothing adds up. The universe does not rush toward its end. It does not choose between silence and event. It simply continues expanding, cooling, waiting with a patience that is not patience at all, because nothing within it experiences the waiting. The Dark Era is not a conclusion. It is a condition the universe will inhabit for longer than everything that came before it combined, and then for longer than that, and then for longer than that again, in iterations that the mind cannot follow, but that the mathematics traces faithfully into distances of time where even the concept of eventually begins to feel strained. And yet the second law of thermodynamics is not cruel. It does not promise suffering, it does not promise awareness. It simply promises equilibrium, the final, perfect, uninterrupted sameness of a system that has distributed all of its energy as evenly as physics allows. Whether that state constitutes an ending or merely a transformation is a question that depends on what you think the universe is for, and that question is not one that physics can answer. It is one that you have to answer yourself. The natural response to everything described so far is resistance. The mind does not accept annihilation easily. It searches for exits. It looks for the clause in the contract that changes the terms, the footnote in the physics that reopens what seemed closed. And so before arriving at what this all means, before sitting with the full weight of what the universe is doing over time, it is worth taking the objections seriously, not dismissing them, not pretending they don't arise, because they do arise in every person who thinks carefully about these timescales, and some of them are grounded in genuine physics rather than wishful thinking. The first and most common objection is this: perhaps the universe does not end in heat death. Perhaps it ends in something else, entirely, something more dramatic, something that resets the conditions rather than simply exhausting them. This is not a fringe idea. Several well-supported cosmological models predict endings quite different from the quiet equilibrium of the Dark Era, and each of them deserves honest examination. The most dramatic alternative is what cosmologists call the Big Rip. The Big Rip arises from a specific behavior of dark energy, the mysterious component of the universe responsible for its accelerating expansion. Dark energy was discovered observationally in 1998, when two independent teams studying distant supernovae found that the universe was not just expanding, as had been known since the 1920s, but expanding at an accelerating rate. This was unexpected. Gravity acting on all the matter in the universe should be slowing the expansion down. Instead, something was speeding it up. That something was given the name dark energy, and it currently accounts for approximately 68% of the total energy content of the universe, more than all matter, visible and dark combined. In the standard cosmological model, dark energy behaves as a cosmological constant, a fixed energy density of empty space that remains the same as the universe expands, producing a steady constant acceleration. In this model, the expansion accelerates uniformly over time, and while it eventually drives everything apart, it does so gradually enough that bound structures, galaxies, solar systems, atoms remain intact until the much longer timescales of stellar death and black hole evaporation take over. But dark energy might not be constant. If dark energy grows stronger over time, if it is not a fixed property of space but a dynamic field that intensifies as the universe ages, then the consequences are far more violent. A sufficiently rapidly increasing dark energy would eventually overcome not just the gravitational binding between galaxies, but the gravitational binding within galaxies, then within solar systems, then within planets, then within atoms themselves. The force tearing space apart would become stronger than every other force in the universe, dismantling structure at every scale in a cascade that ends with even the nuclei of atoms being ripped apart in the final moments before the universe reaches infinite expansion in finite time. This is the Big Rip. It would occur not in trillions of years, but potentially in tens of billions within a cosmological timescale, not vastly different from the current age of the universe. If current measurements of the dark energy equation of state, the parameter that describes how dark energy behaves, indicate a phantom energy component that grows with time, then the Big Rip becomes possible. Current observational data does not confirm this. The measurements are consistent with a cosmological constant, but the uncertainties are large enough that phantom energy cannot be ruled out. Future surveys will constrain the equation of state further, and the answer will determine whether the universe ends in the quiet equilibrium of heat death or the violent dissolution of the Big Rip. If the Big Rip occurs, the heat death scenario becomes irrelevant. There is no degenerate era, no black hole era, no dark era. The universe ends far sooner and far more dramatically, and every structure within it, every galaxy, every star, every planet, every molecule, every atom is annihilated, not by exhaustion, but by the tearing apart of space-time itself. This is a more conclusive ending in some ways and a more violent one, but it is not an escape from ending. It is a different version of the same fundamental reality. The universe does not persist indefinitely in a form hospitable to complexity. Whether it winds down over incomprehensible timescales or tears itself apart in a cosmic instant, the direction of travel is the same. The second major alternative is the Big Bounce. The Big Bounce arises from a different question. What if the universe's expansion is not permanent? What if dark energy weakens over time, rather than strengthening, and gravity eventually reasserts itself, slowing the expansion, halting it, and reversing it into a contraction? In this scenario, the universe would collapse back in on itself, in what is sometimes called the Big Crunch, a reversal of the Big Bang, with all matter and energy converging back toward a point of extreme density and temperature. And if the physics of that convergence allows for a bounce rather than a true singularity, if the quantum gravitational effects at extreme densities prevent infinite compression and instead cause the collapsing universe to rebound into a new expansion, then the Big Crunch becomes the Big Bounce. The new expansion becomes a new universe, with new physical conditions, new structure formation, potentially new possibilities. This idea is appealing in a way that the heat death scenario is not, because it offers cyclicity. It replaces a story with a beginning, middle, and end, with a story that has no end, only an endless succession of cycles, each universe born from the death of the previous one. Some versions of this model, including loop quantum cosmology and various cyclic universe proposals developed by Paul Steinhardt and Neil Turok, attempt to provide a rigorous mathematical framework for how such bounces might occur and what properties the subsequent cycle would inherit from the previous one. The problem is observational. The current evidence strongly favors continued acceleration of the universe's expansion. Dark energy as measured does not appear to be weakening. The universe does not show signs of a future deceleration that would lead to contraction. This does not rule out a big bounce with absolute certainty. Future observations could reveal behavior that changes the picture, but it makes the scenario less favored by current data than the heat death trajectory. And even if a bounce occurred, the question of whether the previous universe's history carries into the new one, whether anything of what existed before persists in any meaningful sense after the extreme conditions of a bounce, remains deeply uncertain. A universe born from a bounce is not the previous universe continuing. It is at best a descendant carrying perhaps some statistical imprint of what came before, but no structures, no particles, no memories, no coherent physical legacy of the world that collapsed into it. The third alternative is the multiverse. This is the broadest and most speculative of the exits the mind reaches for. If our universe is not the only universe, if the Big Bang that produced ours was not a unique event, but one of an enormous or infinite number of similar events, each producing a universe with potentially different physical constant, different particle content, different laws, then the end of our universe is not the end of everything. It is the end of one instance in an ongoing process. Other universes are being born. Other universes will persist. The total structure of reality, whatever that structure is, continues beyond the death of any individual universe within it. This is not an unreasonable idea. Several well-developed theoretical frameworks, eternal inflation, the string theory landscape, various quantum cosmological models predict or imply a multiverse of some kind. But the multiverse, even if real, does not change the experience of ending from within any single universe. If the Dark Era is the fate of our universe, then the existence of other universes does not alter what the Dark Era means for everything that has ever existed within ours. Every star that has burned here, every planet that has orbited here, every form of life that has ever arisen here, all of it ends with this universe. Regardless of what other universes may be doing elsewhere, in a structure we can never observe or interact with. The multiverse is an answer to the question of whether reality persists beyond our universe. It is not an answer to the question of whether our universe persists. These are different questions, and conflating them is a way of avoiding the second one. So after examining the exits, after taking the alternatives seriously and giving them the weight they deserve, the conclusion does not change in its essential character. The universe is moving toward an endpoint. Whether that endpoint is the quiet equilibrium of heat death, the violent dissolution of the Big Rip, or the compression of a big crunch that may or may not bounce into something new, the arrow of time points away from complexity and to simplicity, away from concentration and toward dispersal, away from the conditions that make stars and planets and life possible and toward conditions that do not. This is not a flaw in the universe. It is not a tragedy in any cosmic sense. The second law of thermodynamics is not malicious. It does not choose to end complexity. It simply describes the statistical behavior of systems with large numbers of components, and the universe is the largest system there is. Entropy increases because there are more ways to be disordered than to be ordered, and given enough time, systems find their way to the more probable states. The universe's long journey toward heat death is not a descent into wrongness. It is the completion of a statistical process that began at the Big Bang, when whatever mechanism produced our universe also produced an initial condition of extraordinary low entropy that has been unwinding ever since. But here is where the question of meaning becomes unavoidable, and where physics, having done everything it can, must hand the conversation to something else. What does it mean that all of this ends? Not ends in the distant future in a way that can be safely ignored, but ends with the certainty and the specificity that the calculations provide 10 to the 100th years, 10 to the 10 to the 76th years, timescales that are enormous, but not infinite finitude disguised as forever. What does it mean that every photon of light that has ever been generated in the history of the universe will eventually be so redshifted by the expansion of space that it carries essentially no energy at all? What does it mean that the universe will reach a state in which nothing of what existed before, no structure, no pattern, no record, no trace, persists in any recoverable form? The physicist's answer is that it means nothing in the technical sense. Entropy at its maximum carries no information about the states that preceded it. A universe at heat death is not a universe that remembers itself. The record is erased, not damaged, not incomplete. Erased in the sense that the final state is consistent with an infinite number of prior histories, and there is no way, even in principle, to reconstruct which history actually occurred. The past becomes inaccessible not because it is hidden, but because the physical distinction between one past and another has been averaged away. This is what makes heat death different from other kinds of ending. A supernova leaves a remnant. A civilization that falls leaves ruins. An organism that dies leaves matter that becomes other things. These endings preserve something, not the original structure, but the material from which it was made, which can and does become other structures. Heat death preserves nothing in this sense. The matter is still there in principle, as scattered fundamental particles drifting through expanding space. But the differences that gave that matter, meaning the arrangements that made it a star or a planet or a molecule or a thought, are gone, irreversibly averaged into uniformity. And yet, the universe, in producing life, in producing specifically a form of life capable of understanding its own fate, has done something that has no obvious necessity to it. There is no law of physics that required the universe to produce creatures capable of calculating the timescale of their own extinction. There is no thermodynamic principle that demanded self-awareness as a step in the journey toward equilibrium. And yet here you are, having followed this argument across timescales of 10 to the 100th years, understanding it, feeling the weight of it, perhaps feeling something that resembles grief or wonder, or both simultaneously, in a combination that has no clean name. That capacity to understand the universe well enough to know what it is doing and where it is going is not nothing. It is in fact one of the most extraordinary features of reality that we know of. The universe has in at least one location become aware of itself. It has produced structures capable of measuring its own age, mapping its own structure, predicting its own fate. Whether this awareness matters in any ultimate sense, whether it changes the outcome, whether it carries any weight against the arithmetic of entropy, is a question that physics cannot answer. But the question itself is worth sitting with, because the alternative, deciding that the ending makes the present meaningless, is a conclusion that the evidence does not support and that nothing about the physics requires. The fire of a candle is not less real because it goes out. The music is not less beautiful because it ends. And the extraordinary improbability of a universe that produced among all its possible configurations, one in which matter arranged itself into beings capable of asking what the universe means, that improbability does not diminish because the universe will eventually forget it happened. If anything, it makes the present more remarkable, not less. Step outside tonight if you can, or simply close your eyes and imagine it. The sky above you dark between the stars, each point of light a fire burning at distances so large that the light reaching your eyes left its source years or centuries or millennia before you were born. Some of those stars no longer exist. They burned out long ago, and the light you see is a message from something already gone, traveling across space for longer than human civilization has existed, arriving at your eyes in this specific moment, in this specific life, on this specific evening. You have just traveled in the span of this journey from that light to its absolute end. You have seen what happens after the last star exhausts its fuel and cools into darkness. You have seen the Degenerate Era, the long twilight of white dwarfs and neutron stars, cooling over quadrillions of years in a universe growing emptier and colder with every moment. You have seen the black hole era, those incomprehensible spans of time, 10 to the 100th years and beyond, during which the only objects still evolving in any meaningful sense were the black holes, themselves slowly dissolving through Hawking radiation into. You have seen the dark era, the vast, almost featureless expanse of near maximum entropy through which the universe will drift for durations that reduce all of stellar history to a rounding error, populated by nothing but scattered particles and the fading memory of heat, expanding outward into a darkness so complete that the word darkness itself feels inadequate. And now you are back here, in the present, under a sky still full of fire. The sun rose this morning. It will set this evening. It has done this from the perspective of any observer on Earth's surface approximately 1.6 trillion times since the planet formed. It will do it approximately 1.8 trillion more times before the sun's hydrogen runs out and the sequence ends. Each of those sunrises represented approximately 8 minutes of light travel time from the sun's surface to your eyes. 8 minutes during which the photons produced by fusion in the solar core streamed outward across 93 million miles of space and arrived at the thin shell of atmosphere surrounding this planet and scattered into the blue light of morning. This is ordinary. It happens every day, and it is measured against the universe's full story, almost incomprehensibly rare. The Stelliferous Era, the full age of stars, spans roughly 100 trillion years. Of that span, the window during which a star like the Sun can exist is only a few billion years on either end, because Sun-like stars require the heavy elements produced by earlier stellar generations and burn through their fuel too quickly to survive into the era's later epochs. The window during which a planet like Earth can exist in a stable orbit around such a star at the right distance for liquid water, with the right chemical composition for complexity, is narrower still, and the window during which that planet produces organisms capable of looking up at the sky and understanding what they are seeing, of tracing the light back to its source and forward to its end, may be narrower, still measured perhaps in millions of years, perhaps in less. You are in that window right now, not approximately, not roughly. Right now, in the specific moment of reading this sentence, the universe is in the phase of its existence that produces light and warmth, and the energy gradients necessary for everything you have ever experienced or known or loved. Every meal you have eaten was powered ultimately by sunlight. Every thought you have had was produced by a brain running on chemical energy that traces its origin back to photosynthesis, to the absorption of solar radiation by organisms that converted it into the molecular bonds that became the food chain that became you. You are in a very literal physical sense made of starlight, not metaphorically. The atoms in your body were forged in stellar interiors across billions of years of cosmic history, and the energy animating those atoms right now flows from the nearest star through a chain of conversions that connects your existence directly to nuclear fusion. The universe did not have to produce you. Nothing in the laws of physics required it. The initial conditions of the Big Bang, the specific values of the fundamental constants, the particular history of star formation and galactic evolution and planetary geology and biological chemistry that led from a hot dense plasma 13.8 billion years ago to this moment, none of it was guaranteed. None of it was inevitable in any strong sense. There are vast regions of the possible universe that would never produce complexity of any kind. There are universes in the theoretical landscape of possible physical laws where atoms cannot form, where stars cannot ignite, where the conditions for chemistry do not arise, and the long patient work of evolution has no substrate to operate on. This universe produced all of it, and it produced in the process creatures aware enough to notice. This is the thing that the journey through cosmic time reveals if you let it settle fully. Not despair, not smallness, something almost exactly opposite. Consider what it means to understand the fate of the universe. To follow the mathematics of Hawking radiation through 10 to the 100th years of black hole evaporation, to grasp the concept of entropy and trace its implications forward to heat death, to know with the precision that physics provides that the last black hole will evaporate in a final burst of gamma radiation and leave behind a universe of drifting particles thinning toward perfect equilibrium over timescales that dwarf every other number in the story. To hold all of that in your mind simultaneously, the beginning and the middle and the end, and to feel the weight of it. No other process in the known universe does this. Stars do not know they are burning. Black holes do not know they are evaporating. The expanding universe does not know it is expanding. The fundamental particles drifting through the dark era will not know they are drifting. The process of cosmic evolution across all 10 to the 100th years of it and more proceeds without witness, without understanding, without anything that could be called awareness, except in this one location, in this one era, in this one narrow window of the Stelliferous Age, where matter arranged itself into a form capable of looking back across time and forward into the dark and comprehending the shape of the whole. You are that arrangement. You are the universe's capacity for self-knowledge present in the only moment when it exists. This does not require the universe to have intended it. It does not require meaning to be built into the laws of physics or consciousness to be a fundamental feature of reality. It simply requires noticing what is actually the case, that in the full span of cosmic time, from the first ignition of the first star to the evaporation of the last black hole, the window during which anything in the universe can understand, the universe is extraordinarily brief, and you are inside it. Not approaching it, not looking back on it, but inside it, living in the era when the lights are on and the mathematics is legible, and the distance between now and the last light is still measurable in numbers that, while large, are finite. The stars above you tonight are not a permanent backdrop. They are a temporary condition, a brief, extraordinary flourishing of nuclear fire in a cosmos that was dark before they formed and will be dark long after they fade. The warmth you feel from the sun, from the food you eat, from the chemical reactions sustaining your body, is borrowed from a budget that is being spent slowly but irreversibly with every second that passes. The energy gradients that make thought possible, that make music and mathematics and love and curiosity possible, are the product of a low entropy initial condition established at the Big Bang and being unwound over cosmic time in accordance with the second law of thermodynamics. None of this makes the warmth less warm. None of this makes the light less real. There is a tendency when confronting the scale of cosmic time to feel diminished, to feel that the brevity of human life, or even of stellar life, against the backdrop of 10 to the 100th years of black hole evaporation and 10 to the 76th years of the dark era, renders the present somehow less significant. This is a natural response, and it deserves to be acknowledged rather than dismissed. The numbers are genuinely overwhelming. The scale of what comes after the age of stars is genuinely beyond the reach of intuition. But consider what significance actually requires. It does not require permanence. It does not require that the record of an event persist forever for the event to have been real. A supernova that occurred 5 billion years ago and left no remnant detectable today was still real. The light it produced was real. The elements it scattered into space, which eventually became the material of stars and planets and living things, were real. The fact that the universe will eventually reach a state in which no information about that supernova survives does not retroactively diminish what it was. The past is not made unreal by the future's inability to remember it. This applies to everything that has ever existed. Every civilization that has arisen on any planet around any star in the history of the universe. Every moment of awareness, however brief, that has occurred in the Stelliferous Era. Every act of understanding, every measurement of cosmic structure, every calculation of stellar lifetimes and entropy gradients and Hawking radiation. These things happened. They were real. In the only sense that anything is real, they occurred, they were experienced. They left their mark on the state of the universe. At the moment they occurred, even if the universe will eventually reach a state in which that mark cannot be distinguished from the background, the ending does not erase the having been. What the journey through cosmic time ultimately offers is not consolation in the face of ending, but a reframing of what the present actually is. The present is not a pale shadow of some more permanent reality. It is the reality. It is the window. It is the narrow, extraordinary, statistically almost impossible era in which the universe is warm enough and bright enough and complex enough for awareness to exist within it. Every moment of that awareness, however fleeting measured against 10 to the 100th years, is not a moment of impermanence. It is a moment of the universe experiencing itself, the only moment that experience is possible. The last light will come, not today, not for billions of years, not for quadrillions of years, not until timescales so large they require entirely different mathematical notation to express. But it will come. The last red dwarf will cool into a white dwarf and then a black dwarf, and then eventually into something that may dissolve through proton decay or persist as frozen matter, until quantum tunneling collapses it into a brief black hole and a final burst of Hawking radiation. The last black hole will evaporate in a flash of gamma rays in a universe so old that the number of years it has lived cannot be written in any conventional notation. And then the dark era will continue, and the scattered particles will drift, and the universe will expand toward equilibrium, with a patience that is not patience at all, because nothing within it is waiting for anything anymore. The warmth is here now, not there in that distant end, not preserved in some cosmic memory that will outlast the dark era. Here in this moment, in the fire of stars that are still burning, in the energy flowing through living systems on at least one small planet, orbiting one middle-aged star in one galaxy, among hundreds of billions, in the awareness of a creature that has followed the universe's story from its luminous beginning to its silent end, and chosen to sit with what that story means. The light you see when you look at the stars left those stars years or centuries or millennia ago. It has been traveling toward you across distances that dwarf anything else in human experience, through the expanding darkness, between galaxies, through the thin atmosphere of this fragile planet, arriving at your eyes in this specific instant as part of a universe that is against all probability, still lit. It will not always be lit, but it is lit now. And that the extraordinary, temporary, irreplaceable fact of now is not diminished by knowing what comes after. It is clarified by it. The universe does not need to be permanent to be real. The light does not need to last forever to illuminate. The fire does not need to burn through the dark era to have mattered in the moment it burned. You are standing in the light of stars that formed from the death of older stars on a planet made from the ash of stellar explosions, aware of your own existence in a universe that had no obligation to produce awareness, and produced it anyway in a window of cosmic time so brief that measured against the full span of what comes after it is less than the blink of an eye. And yet it is everything. It is the only moment the universe will ever know itself. A single candle burning in a darkness that stretches farther than light has traveled since the beginning of time, not despite the darkness, because of it. The warmth is here now. It is extraordinary. It is temporary. And it is ours.